lecture. I'm not going to introduce Alain, but I'm just delighted that he's here as the Rothschild Fellow for approximately a month, and he is here as part of one of the I&I programs. Eric is going to say a few words about the program, and then Ray will introduce Alain. So thank you very much for coming, and I'm sure it'll be a fantastic lecture.
Thank you, David. So before moving on to the talk, I'd like to give you a little bit of context of this talk. Professor Goriely's talk is one of the main public events as part of a 4-month program we have here at the Institute called Growth, Form, and Self-Organization. And the idea, there are 3 main co-organizers, I'm one of them, and the idea was to bring together researchers from different strands of research that all deal with shape. And so that brings together biologists in particular, physicists, and mathematicians. And the program is for 4 months. There are 4 workshops. There's a seminar series. We have 2 seminars per week. And there's a lot of long-term visitors who are here at the Institute, sitting somewhere upstairs, and they're here for a few months. And so I hope that tonight's lecture will inspire some of you to come to some of our events. And that's all I want to say. And I will let Professor Goldstein from them introduce our speaker.
Thank you, Eric, very much. Well, it really is a great pleasure to have the opportunity to introduce today's speaker, Alain Goriely from Oxford, someone I've known for several decades as a colleague in Arizona, as a collaborator, and more recently as a distant collaborator and colleague in Oxford. Belgium, as you know, is famous for many things. Fine chocolates that we all like to pick up when we're changing trains on the Eurostar. And, for instance, the famous detective, Hercule Poirot, from Agatha Christie's novels. And Alain, in some sense, is a sleuth of a different kind. A mathematical sleuth who has been able to find in the natural world over many years a whole beautiful range of problems to tackle that have not only real interesting, difficult, challenging mathematics in them, but a real aesthetic that I think is perfectly captured by the theme of this talk and this whole program. So after his PhD in Belgium, he moved eventually to the University of Arizona, where he rose through the ranks to become a professor of applied mathematics. In 2009, he moved to Oxford, where he's been in leadership positions both in Occam and Occam since that time. And his work has ranged over a huge range of subjects, everything from the tendrils of climbing plants and how they coil and attach to supports, to the patterns of the umbilical cord, which have a similar kind of structure. More recently, he's been working on issues associated with brain injury and the swelling of tissues, and how one might actually use mathematical techniques to try to help doctors understand how better to treat patients with issues like that. So I don't want to dwell on all his wonderful accomplishments too much, but I do want to say that many of us, Alain, myself, and others in this audience, have always been inspired by this wonderful book. See, I thought I was being clever by bringing a copy of D'Arcy Thompson, but there are better copies here. But one of the things that you find when you look through the scientific literature is that many people love to quote old books just to sound important, but few of them have actually read everything inside those books. But today's speaker really, really has read and deeply understood the lessons of D'Arcy Thompson. So, Alain, we look forward to it.
Thank you, Ray. I'm a little speechless now. Before we delve into the work of D'Arcy Thompson, I do have to express my gratitude to the Isaac Newton Institute, the director or the program organizer of this wonderful program, to Trinity College and Keith Moffat for his hospitality, to the Rothschild and Sons for the generous support. And also, I'd like to thank the Rhine Library at Trinity College that allowed me to bring some of these things here, and the Museum of Zoology here also in Cambridge that allowed me to take some of the wonderful specimens out. We'll get to that in a minute, but first we'll have to learn a little bit about D'Arcy Thompson, the man. So D'Arcy was born in 1860. Here you see he's about 10-year-old. Just showing you this picture to show you that not all great professors are born with a beard. He was born in Edinburgh and went to the famous Edinburgh Academy, where his father was teacher before he moved to Galway. In 1880, he moved to Cambridge as a student at Trinity College. So let me tell you a little bit more about his time, since it's fitting to the place where today. So 1880 Cambridge was quite different, as you can expect from nowadays. Here is the marketplace 2017, and here is 1880. You see people wear hats. Oxford won the boat race that year. It was the only time in all its history that the boat race was delayed by 2 days because of the fog. Here is the Senate House today, with people and tourists taking selfies, and here is the Senate House in 1880. And you see they had horses. Cambridge had already 21 of its college, population of 30,000, rapidly growing. The steam revolution was coming, fields were plowed by steam engine and so on. For somebody coming from Edinburgh, it was looking at the great technological revolution. It is in this Senate House that young D'Arcy, in 1882, at the end of May, would climb over the fence at 11 at night with a box of matches and candles to go see his result from his tripos. They were posted at 11 p.m. that night, and he got first class. He got first class in zoology, which is roughly the equivalent of natural science today. It's also in the Senate House that 1 year later he came back to listen to a talk, the Reed Lecture, very important lecture at the time, still is, but it was more on the science at the time. And the lecture was by the formidable Thomas Henry Huxley, was president of the Royal Society and authority in the land, also known as Darwin's bulldog for his famous debate against Sam Wilberforce, Soapy Sam, in 1860 in Oxford. And his talk, D'Arcy made great impression to D'Arcy. He recounts many years after, that Thomas Huxley, the Senate House was filled and Huxley stood before us with the Nautilus in his hand. And as you know, the Nautilus, you saw it on the cover of Ray's edition, Dover edition, and the Nautilus is a parable for a lot of D'Arcy's work, and it's also a parable for Thomas Henry Huxley's work. He used it as showing evolutionary process. Now, the time that he spends was marked by great people at the time. It was a golden age for science, much like it is nowadays. He took physics, electricity and magnetism from Lord Rayleigh, and he was greatly influenced in biology by a number of researchers, especially Michael Forster, student of Huxley, and Frank Balfour, extremely bright young man. Also at the time, Alfred Newton made great impression on him, and you might see all his name as you go around Cambridge, the Newton-Balfour Library, for instance, and so on. Now, not only was it a great time for research, it was also a great time for educational change. Michael Forster has this revolutionary idea that it may be good for students that after theoretical lecture, they also have labs where they can actually practice and learn biology with hands-on. And it was perfect for D'Arcy Thompson, who always loved nature and always loved to look at things in detail. Unfortunately, Frank Balfour, who was the brightest of them all, according to many, the heir apparent to both Huxley and Darwin, died tragically in 1881 in a climbing accident in the Mont Blanc. That left a great effect on many, but things carry on. Adam Sedgwick took over, and things move on for D'Arcy Thompson. But, as you know, Cambridge is not just a university, where there were great change at the university. What mostly was Cambridge for D'Arcy Thompson was Trinity College. I don't have to show you a picture to show you that it hasn't changed that much. You all recognize the master's lodging and the chapel here. And this is what young D'Arcy says when he arrives at the place. The college alone is like a town. 600 men dine in all every day. The kitchen would hold a small university. And by the record, in his second year, after coming as a sizer, the poorest type of scholarship that you could afford, that you could get, He won a very prestigious scholarship, which allowed him to move rooms. And we know from the record that his room was right there, staircase B. And to be precise, this is where the room of D'Arcy Thompson was. So here is D'Arcy, and to show you how important his college atmosphere was to him, here's D'Arcy with his friends again. And who are his friends? I had to look up a little bit, and his friends here are Alfred Whitehead, famous mathematician, then philosopher, who wrote the second volume of Principia Mathematica with his student Bertrand Russell, Henry Head, famous neurologist, and William Sawley, the philosopher, the Scottish philosopher, well known for his ethics. And you can see the attraction for D'Arcy Thompson, who was always interested in all subjects, from classics to philosophy to literature to physics to mathematics and to natural science, to be in company of all these men and have this type of education. As Alfred Whitehead said, that was the way that Cambridge educated her sons. Whereas his friend, Alfred and William, got a fellowship at Trinity, unfortunately, for some reason, D'Arcy Thompson never got one. And he said many years after, I still love every stone of the place. I came in exultation, I left it in deepest disappointment for never getting into Trinity. Just like his father never got into Trinity either. So it was a family disappointment. And so D'Arcy went. This is Neville's court today. You see, not even the lamp has changed. So, but it was not the end, quite the opposite. It was the beginning for D'Arcy Thompson. He won easily a chair of natural philosophy at age 24 to the new University College Dundee, and moved there and right away got to work and created a wonderful museum. The museum has since then disappeared. In 1917, he moved to St. Andrews, very close by, to take the chair of natural history, kind of academic upgrade, if you want, for him. And there he continued his work, building a new museum of zoology that is still around, and the people in the program will go there, should have a look if they have a chance to go to St. Andrews. And here you see it's the Bull Pettigrew Museum, and here you see the skeleton of an elephant, which we know is the last skeleton that D'Arcy Thompson acquired in his life. He died, age 88, at St. Andrews in his house, having been professor for 64 years. He received many honors, though most of the honors that he received came later in life. In 1916, he became Fellow of the Royal Society, before the publication of A Growth and Form, mostly on the strength of one paper, Morphology and Mathematics, that constitute the last chapter. We'll talk about that in a second. The other honors came later in life, you see, when he was already 77 and so on. People realize its prominence in the field. By most accounts, he was kind. He was dedicated to educate the poor and the worker. He loved children. He was very active in the protection of nature. He had no time for fools. But most important, the effect that he gave on people was his scholarship and his authority, his intellectual authority. And he was said by many people that he had the bearing of a real professor. So that's all something we aspire to. It's very hard to describe what it's actually meant, but this is what is actually meant by that. No, that's the bearing of a real professor, if I may say. This is an authority. Now let me tell you about the book or the books. So it has been 100 years since this was first published. First published in 1917, 793 page, 407 figure. This is actually a first edition that was given on loan to me by the Wren Library. It's the first time I had it in my hand, so I was quite happy. I welcome you to have a look after. By 1922, it was 500 copies were made, and by 1922, it ran out of print. And Cambridge University Press asked him to prepare another copy, a new edition. But he was not quite happy with, the, edition, with the current edition. Hopefully he's going to come back. So it took him another 20 years to complete the revised edition, which contained close to 1,100 pages and 17 chapters. So this one here is not the first print, but close to it in 2 volumes. And of course, you've seen the edition that the edition that we know best, which is the one from Dover, okay, which had the nice Nautilus again. There were other editions made, one an abridged version by J.T. Bonner, who thought that in order to promote the book, he should do a reduced version to try to extract. It's a nice edition because it has a lot of notes by editorial notes to explain aspects of it. But it's not quite as satisfactory as having the real text with all the rich illustration. There is a nice French abridged version also, which is a translation of this one, with a very nice introduction by Stephen Jay Gould. There are other books that are related to that. A wonderful book about D'Arcy Thompson's life by his daughter Ruth, with a very interesting postscript by Medawar. Another book here that is by Le Gros Clark and Peter Medawar, which is a beautiful book. And it's interesting because it's called Essay on Growth, presented to D'Arcy Thompson as an honor. What is interesting is that it's people that are interested, both Le Gros Clark and Peter Medawar. Peter Medawar won the Nobel Prize for his work on immunology, but these are people from developmental biology, physiology, and anatomy, not from regular evolutionary biology. Peter Medawar was quite young at the time, 30, but he was already working quite hard on problem of growth. He was really interested in the mathematics of growth. Now, another book that I didn't bring because it's way too heavy is the book by Stephen Jay Gould, who has a long chapter about D'Arcy Thompson. So the life of Stephen Jay Gould is very interesting because he follows almost his first paper until his last book aspect of the work of D'Arcy Thompson, and always goes back to D'Arcy Thompson. So in many ways, writing this book is the growth and form of Stephen Jay Gould, his opus maximum. Okay, so one last book, that's this one. It's one I wrote recently. So do not think I try to put this book on the same footing as all these other great books, but I wrote it and I'm giving the talk. And more important, I will extract example from it for the talk. So when you'll see Hogarth, it'll be the second edition of the book, and the MOMAB will be, or the MAMOB will be the TIS version. So first question we have to ask before we go any further, was D'Arcy Thompson homo unius libri? Was he the man of a single book? One-hit wonder, as we once say. Well, let's look at his other works. First book is a bibliography of Protozoa, sponge, and other things, which is just a list of papers with some comments. Okay, maybe not most interesting of books. His second book was a glossary of Greek birds. Now, this is interesting and was highly acclaimed by critics. D'Arcy Thompson has a love for classics and goes into the Greek literature and identified every single bird that appears in Greek literature and say, well, when you see this bird, this is the March tit. Or you see this bird, this is an eagle in the fable of the fox and the eagle by Archie, and so on. Okay, so greatly acclaimed by specialists, but maybe not the bestseller, as you might think. His other works with about 300 articles, letter, remark, translation, and comment. About 40 of these are actually in the journal Nature, which would make him a very prominent scientist nowadays. But at the time, letters to the journal Nature were letters to the journal Nature. You know, here is I saw something on the beach. Like, here is the note on a dolphin showing traces of an encounter with a cuttlefish. You know, beautiful illustration. Or this other paper on the pteridiosis of the giant hummingbird, which is the place where the feathers are placed. This beautiful drawing. And so on. Many translations, many comments, many reviews of book. He was extremely prolific in many ways, but nothing that stands the test of time. His latest book, very nice way of finishing, was the glossary of Greek fish. I don't think I have to explain to you what's in there. So yes, if it wasn't for growth and form, I don't think we would be talking about D'Arcy Thompson, and he would be forgotten from history. So let's get into the book itself. What are the themes and the thesis? It's well known, many people quote this preface. He says, "This book of mine has little need of preface, for indeed it is all preface from beginning to end. I've written it as an easy introduction to the study of organic forms by methods which are the commonplaces of physical science." So what does he need like that? He goes on. His main idea is that natural science needs a mathematical foundation. And he says, just as the astronomy of Newton and Laplace, we have to put natural sciences on a foundational level. Right? So it's very, and he says explicitly, the goal is to have theoria philosophia naturalis. Right? A general theory of natural philosophy, much like his friend Alfred Whitehead did with Russell on the mathematical principle. So the main idea of the time, if you look at the biology and the zoology, was mostly heredity and evolution. By 1880, by 1885, the battle for evolution had been fought by people like Huxley and largely won. So now the point was to try to develop this idea of evolution, to build the phylogenetic trees. And the question is always why animals and plants the way they are, trying to explain that to evolutionary ideas. And D'Arcy has issues with that are partly justified. The issue is what is called teleology, or teleological argument, which is the final explanation of phenomenon by reference to its purpose. The tiger has stripes because it aids to its camouflage, and so on. Right? And he says the teleological argument pervades Darwin's whole train of reasoning. I think that's partly true. It also pervades D'Arcy Thompson's train of reasoning. He has an entire chapter on mechanical efficiency, for instance. And it's an argument that you cannot really avoid eventually in biology. You know, they try to construct sentences around theory and all that, but by the end, it's a natural human instinct to know why. And when I give a talk about the mechanics of biology and explain a mechanism, people will always ask you, yes, but why is it like that? Why? Because we want to know why. But for D'Arcy, this is not the same. He says he wants to change the question. He says, why is okay, but let's think about differently. And so here's what he says. In Aristotle's parable, the house is there that men may live in it. But it's also there because the builders have laid one stone upon another. It is as a mechanism that the physicists look upon the world, and Democritus choose to refer all natural phenomena to mechanism and set the final cause aside. So what he's telling you, he says, yes, you can decide why the house is there. What I want to know is how the house is built, right? How is a structure formed? How can we describe it? And he has to fight for this question because nobody else wants to ask this question. Another issue that he has is what's called vitalism or entelechy, is that the belief at the time, and for a long time before, going back to the description of urea, for instance, is that biological systems depend on force that are purely distinct from purely chemical or physical forces. There is something special about biological systems that cannot be described by physics or mathematics. And it was really encroaching at the time, and it's still to a certain extent when you discuss in biology, people will tell you at some point, yes, physics may be useful, but you know, biology is just too complicated for physics or mathematics. It's still a battle in many ways that we have to fight. And I'm sure anybody who's done mathematical modeling has come to this kind of view before. And what does D'Arcy Thompson says about it? He says, well, again, it's about the question. I do not ask of physics or goodness shine in one man's face and evil betrays itself in another, but of the construction and growth and working of the body, physical science is, in my humble opinion, our only teacher and guide. Okay, so what he proposes is a physical foundation of natural science, and this must be achieved through mathematics. By physical theory, what he really means at the time is mechanics. Well, mechanics is the queen of physical theory for the 19th century, the reference, or to build a theory. He has two themes, essentially, if you want to boil it down. Geometric simplicity, on one hand, and forces, shapes, organisms. And in there, he's trying to be the student of both Kepler and Newton. Kepler, who described orbits, identified the patterns, and he's trying to do the same for many biological forms. But also Newton, He says, well, if you want to understand orbits, you have to start with the equation and how forces act on particles. And there maybe is less successful, as we're going to see. He says, my sole purpose is to correlate with mathematical statement and physical law certain of the simpler outward phenomena of organic growth and structure of form. Okay, so let's start in more detail on growth now. And he starts with growth because he says, growth deserves to be studied as a necessary preliminary to the theoretical study of form. You have to start with growth. So the first thing you want to ask when you look at the evolution of growth is what the evolution, the mass of an animal, of an individual, right? And it was in 1920 that Putter put forward the proposal that growth is really a balance between addition of mass and removal of mass. And this is contained in this equation, differential equation, logistic equation. So if you have b equals 0, you see that this is just exponential growth, right? But with this extra term, you reduce the effect of growth. It's one of the two principles that Peter Medawar tried to extract from basic growth. His first rule was that what results from biological growth is itself capable of growing. And that's the first part of the equation. His second rule is that the acceleration of growth decreases in time. And that's the fact that it decays in time. Like that. So this is figure 80 from, on growth and form. And D'Arcy Thompson, it's the only ordinary differential equation, the only differential equation you will see in D'Arcy Thompson. It appears in two different pages, and I don't think D'Arcy really realized it was the same equation. This is the growth of sunflower stem, right? So in the first edition, there is no differential equation, and I don't think he was aware at all of differential equation, because we have a very nice piece of history given to us by Walter Lederman, who was a brilliant mathematician, immigrant from Germany to St. Andrews, and was a colleague of D'Arcy Thompson in St. Andrews. And Walter Lederman recounts, one day when he saw me in the university library, he said, "Do you know anything about differential equations?" When I replied that I was familiar with the usual fact in this subject, he put his arm on my shoulder and said, "Here is a good boy. Come along with me to my house and tell me all about it." So I went to his house with him, sat down at his desk, and wrote out the answer to his question. So we know that the learning, the teaching of differential equation was an afternoon with Walter Lederman on that. So that's where we know. So there is quite a bit of mathematics on growth in this book, but there is really no modern mathematics or even old mathematics for the time, right? It's really, most of it is classical mathematics. However, there is one thing that he's very good at, is understand scaling relationship. Now, once you know that our mass evolved, that's the basic thing you want to know, you want how different quantities evolve with respect to mass. No, you don't have to solve a differential equation, you just have to compare. So, the first question is how mass is related to height. And that you find, it's quoted in D'Arcy Thompson, in Adolf Kettler's Treatise on Man. So Kettler was a Belgian polymath. And his book is quite exceptional also because it's the first book where the Gaussian distribution is used in a statistical setting. It's also the first one to study in detail population and height and mass and so on, and the first case of an allometric law. So the allometric law, the idea is you relate, let's say, mass, total mass, to height up to a power. And this is very well shown in D'Arcy's book. If you plot height, you have this curve. If you plot weight, you have this other curve. Now take height to the cube, essentially you see that these curves are almost the same up to a constant. Okay, and that constant is here, that's C, and the alpha in this case would be 3. Okay, that was already contained in Kettler's book, and it's known as, C is known as the Kettler coefficient, and also known as the infamous body mass index. Right? That's an example of an allometric law, which is the relation between any quantity and the total mass of an organism. So scaling is very important, but relative scaling is also important. You can do that with the height, but you can look at the relative growth of different parts of the body. For instance, the head as growth proceeds. And so the idea is that different parts of the body grow at different rates. That's why you can easily recognize a picture of a baby from the picture of a grown man. So the idea is that the mass of part of the body could be related to the mass of the total body. For instance, if you take the claw of this fiddler crab, and you look at the evolution of the mass of the claw with respect to the evolution of the mass of the entire crab, you have this curve from D'Arcy with a power of 1.62, right? Alpha equals 1.62. Now, this idea is quite profound in many ways and was picked up by Julian Solé Huxley, the grandson of the first Huxley we saw. In his book, Problems of Relative Growth, we go into detail, finding many, many examples and building the theory for the scaling of growth. And on the front page, he writes, I owe a great deal to previous work in this field, first and foremost to D'Arcy Thompson, who put it so nicely in Growth and Form. Now, this idea is probably one of the top contributions of mathematics to biology. The entire field of biology that use this idea in comparative anatomy, in ecology, and so on. It's one of the main tools. You have an entire book built around just measuring things and trying to find in log-log plot lines and find numbers and try to deduct something about first principle from these studies. But D'Arcy realized that there is something very important about scaling, and that's what is important is size matters. And here, give you an example. In the 17th century, people used to discover dinosaur bones, and they would misattribute them to older men, giants of the past. So if you have a bone of dinosaur and you say, well, that's the bone of the foot, and you scale it up, that's what it would look like. That's a bone found in Sicily, for instance. Right? That's in Kirker's book. There are a lot of illustration compared to the ordinary man. But at the time, Galileo already knew that nature cannot produce a horse as large as 20 ordinary horses, or a giant 10 times taller than an ordinary man, unless by miracle or by greatly altering the proportion of his limb and especially of his bone. Right? It is the famous picture of Galileo comparing different bones. He says, if you want to resist buckling under your own weight, as you increase the size of an organism, you also have to increase the width of the bones. Otherwise, you'd buckle. It's the 3/2 law in this case, in the allometric sense. Why is that important for D'Arcy Thompson? Because he reached an important point. He says size matters. We call a thing big or little with reference to what it is want to be. We speak of a small elephant or large rat. Well, that's an interesting comment. But here is the conclusion that he reached. We are coming to a conclusion which will affect the whole course of our argument, namely that there is an essential difference in kind between the phenomena of form in the larger and the smaller organism. In the smaller organism, we have reached an order of magnitude in which the intermolecular force strive and altogether outweigh the force of gravity, the prevailing factor in the larger material aggregate. So what he's doing, in a sense, is what physicists do every day when they first look at a problem. Like, what are the typical length scale of importance? What are the forces that really matter for this problem? He says in the small, very small organism, gravity is not going to play a role. In the very large one, intermolecular interaction is not going to play a role because they'll be secondary to force of gravity. It's completely obvious to us now, but it was very nicely put by D'Arcy 100 years ago. So he's going to use that, and now we'll talk about form. Form in 3 parts. Part 1, analogy. Here is walking the street of St. Andrews with his wife Maureen. Analogies. He's trying to build out of this idea of separation of scale for force, he's trying to understand form now. Can go to the next step. He has an understanding of growth, let's go to form. And what he's going to use is a trick, or not a trick, but a way of thinking that's very typical for the 19th century. We call them Victorian analogies. It was a time where you use analogies between physics and other fields in order to extract idea or new theory. This is what Maxwell used when he wrote in 1855 the first paper on Faraday's force by analogy with fluids, and that's why we think of current, in electrical current, as a fluid. It's a current. It's also what Darwin used for his evolutionary theory by analogy with the evolution of language. The same is true. So the way D'Arcy uses it is as in the microscopic world, we know surface tension dominate, and if you look at a droplet, it is the balance of force right at the interface between liquid, solid, and gas. And we know you're from Young-Laplace law and other laws like that, that we can find the form and the contact angle from physical problem. He says the same apply to cell on the dragonfly, the wing, or various cell. And his argument is actually very good, and it's something that we still use nowadays. When we try to build theories, like in this paper, of imaginal disk wing of Drosophila, these are the theory that I use. This is exactly the idea that allows you to go and start looking at evolution and division of cells based on idea of surface tension. It's a good and still workable basic principle. That form at this scale may be due in many systems largely to force related to surface tension. Now, when he looks on the other side, where gravity dominates, he looks at example like bones, and this is also well known. There's a lot of biomechanical law from the late 1880s to 1890s, such as Wolff's law, that tells you that there is an adaptation of tissue or bones to external mechanical law. So what Wolff's law said, by analogy to Coleman's crane, is that bone adapt by reinforcing in order to resist the load. So the basic idea, and you can run that, here is a simulation of that process. If you start with an homogeneous uniform bone, you can adapt the density by reaction of the force felt at some point. And so there's increase in density where you need to have the more resistance. These are still the basic idea that I use in biomechanics nowadays for a problem of evolution and growth. So these work perfectly fine. It goes on and says, here is a well-known, the diagram of the Stegosaurus, and it compares it to a bridge. Okay. It says, in short, the form of an object is a diagram of force. Yes, we can see it's a diagram of force, but what does it really tell us? This is where the analogies start breaking down. And to tell you that analogies don't always work, well, let's look at another example. Here's the problem with analogies. Here are various species of Lagena, and here are Roman pottery for comparison. It says, okay, so what do we learn by analogy of the Roman pottery about these? So in case you want to know what Lagenas are, I'm sure you're all very curious, it's a genus of foraminifera of the superfamily Nodasariaceae. So these are protist millimetric organisms that have a single cell wall and calcite skeleton, and that's what's left of them. Not the most studied organisms, but they're very nice shape. It's very hard to find anything about them. So what do we learn about these? By analogy. It's hard to read when you read D'Arcy Thompson to extract something from there. That's where the analogies break down. I'll give you another example, maybe more current. Here is a snail that was recently discovered in India, and it looks very much like Harry Potter's sorting hat. And this is why they call it Gryffindori, the species guy. So I don't think they really mean that they're really learning something from the way people make hats in order to understand the shape or form of this animal, right? So analogies, yes, but what can we really say? Let's go back to D'Arcy Thompson. I'll try to put the idea to the test. And sorry for the punt. So one aspect of that is that D'Arcy Thompson looked at the sea urchin shells, which, by the way, are called test. So this is a test, the test of a sea urchin. He compares them to drops. And he says we have little difficulty in saying that the various forms represented in a series of sea urchin shells are no other than tools which we may easily and perfectly imitate in drops. So know that all very well. So I got these when I was vacationing on the Jurassic coast. I said, let's put it to the test. I know the equation for these. Let's try to, there's only one parameter, capillary length over O. And let's try to put it to the test. And I did a fit, and it fits very well. So I said, whoa, wait a second. I was happy to disprove the theory, but you try with other ones, and actually it works very well. Here's a three-dimensional shape. And we also know that T's shape, or T's one, is also realized in engineering dome. This is a classical solution from Timoshenko, where you try to find an optimal dome that best resists the pressure of water. So what's going on between all T's? Clearly, this is very different. This is full of fluid. This is a solid membrane, right? So how do we reconcile the two? Well, we know that the physical shape of a sessile drop is due to the physical force of gravity. That we understand. It has the same shape than the biological shape, at least by observation, and you can refine that, but it's very close. So D'Arcy Thompson would try to connect the two directly, but we have to be precise now, or we have, in a modern view, we try to find the mechanism responsible for a shape, not just an analogy. So the idea now is to look at a growth process that is stress-driven in this organism, and you can build a theory out of these two, and what you obtain is a mathematical model that has a generic solution, and that generic solution is the same as the one that we had before. So it's an example of what we call no convergence. Different theories might lead to similar equation, maybe based on fundamental principle of physics or symmetry or other things like that. What we learn from this example is that if we want to have a growth process that gets to the right shape, if it is the same shape, then it requires a particular growth law that balances surface stresses during development. That means there must be, at the cellular level, some mechanism that balance stress or line tension in two different directions so that they become equal in the final shape. So we do learn a little bit by this analogy. But these analogies can only go so far. What distinguishes an eagle from an hippopotamus? They're both subject to gravity and all that. So at this point, D'Arcy goes to the next step. He says, well, okay, now I'm going to go try to do something else. I'm going, just like Kepler, try to find the ideal shape of an organ. And you see here with a lobster. He was known to always lecture with some props and some animals, some that he found in the market, or dead seagull coming to class and ask the student to tell him about it, or a fish or something like that. So what about ideal shapes? Where D'Arcy is looking at the world around him and just trying to describe, just like Kepler, trying to find the right equation just by having a good guess. Okay, so here is an equation, simple equation. He's actually quite good with the different geometry of polyhedra because of his classical training. He's really a Greek mathematician in many ways. He has a mathematical paper on classification of shapes, actually. So with that, it's quite good. There are plenty of other examples. The one known, or the best known, is the logarithmic spiral, right? The spira mirabilis that he found in T's, that were first found by Reverend Moseley in 1838, first described. And if you take, for instance, T's, the Turritella, I invite people to come and discuss with me after the talk, T's, I'm going to pass them around. But if you take the Turritella, or maybe even more interesting, one of the Turritella that I got from the Museums of Zoology that date from Victorian time and that might have been used by Huxley during his talk, as we know he had plenty of them. So all these might have been on the Senate House table 120 years ago. So if we take that and you measure markers, it's remarkable that it's an extremely good fit to the logarithmic spiral, right? And it's the logarithmic spiral that captured the imagination of so many people, so many philosophers, and Goethe and other, and Cook, for instance, we see them everywhere. So it's also very limiting because the way we do it, we approach the subject from outside. We look at it and we're trying to fit a shape. We know nowadays that the approach, much like Newton, is to go the other way. Try to find the basic mechanism and build out of that the shape. Or see the relation between the law that you have at the local level and the shape that you obtain at the global level, the overall shape. So the modern view that we have now is that if you look at an active seashell growing, you have an active mantle here, and that this curve will in time accrete another curve every time the mantle or the soft body animal comes out, the mollusk comes out, accrete, put another layer, and create layer after layer after layer. And this is how you can generate curves, or even generate more complicated shapes. This is a beautiful example from the Wren Library of excrescency, outgrowth of a deer antler that was given by William Mainstone in 1682 when the library was first started. So we can push this idea and really start building now with simple growth law, find the law that we need at the local level that the cell must obey in order to create this type of structure. And this is the kind of things that I've been working on with Derek Moulton in Oxford. And if you do that, you find plenty of fascinating shapes. Of course, you can play the game, but by the end, it's still a game. You want to go one step further. And one step further, he says, well, now that I have the shell, can I understand other features of these? They are beautiful features like spikes and ornamentation. Even the turritella, if you start looking finer, you'll see it is undulation and wrinkling of shapes. How do we understand that? Another beautiful one is the ribbing that you found in ammonites. Ammonite have disappeared 100 million years ago or so, but beautiful record shows that most of them are all ribbed. How do we understand the ribbing of this structure? And the idea now, you can build a theory out of that, so the wavy ridge and so on. And the idea is that you can follow the same type of law, very simple one, and have the elastic mantle growing on a rigid foundation and laying its own foundation. So the idea is that at any given time, if you have an aperture, the soft body would come out and deposit a new layer. But the soft body also has its own rule of growth. It also expands. So it might not fit properly onto the aperture and start being unstable or buckle around it, right? And so you can, out of a first shell edge, this one is a little longer, so it starts buckling. But you repeat this process just like nature does. Every day, the seashell, the mollusk comes out and put a new layer, and comes out and put a new layer. Incremental process, it builds its own house. And just build on this idea, you can actually do quite a bit in understanding some of these shapes. This is a relatively simple model where you combine the mechanics of the rigid accretion process with the mechanics of the growing soft elastic material that allows you to identify plenty of this shape. So it's a beginning, at least, in the forward to D'Arcy Thompson. So let me go to part 3 now, which is transformation. And probably it is one of the things that D'Arcy is better known for. It's part of his paper on morphology and mathematics. And he realized that he can only go so far in describing ideal shape. How do you describe a skull now with just sine and cosine? How you describe a bone, really, in details. So he's going to attack the problem from a different angle. He says, I'm not going to try to describe the shape. What I'm going to try is describe transformation of shape between two different animals, or two different organisms. And here what he does, he describes it. He starts with a fish like that. He says he's gonna draw the fish there. He says, let us deform its rectilinear coordinate of the parrotfish into a system of coaxial circle. Then filling into the new system, we obtain a very good outline of an allied fish, the angelfish. So he said, if I deform it, it looks like the angelfish. So the two somehow are related. Right? He's going to push this idea. And where does this idea, what does he give credit to? He gives credit to Albert Dürer. Albert Dürer, who wrote his wonderful book in the 16th century. The book is called 4 Books on Human Proportion, where he measures and compares different human proportions. Wonderful. So there is a wonderful way to show you the idea of D'Arcy Thompson as shape of individual transforming from one to the other one through the work of Dürer. It wasn't done by me, but was well done on this wonderful. I can control the sound, so I'll let you enjoy. That's bad. Let's hope it's coming back. Okay, so I don't think so. It's quite wonderful piece of art. It makes you realize this is so nice and simple. I should be an artist. Then you realize you never have the idea in the first place, and that's why you're not an artist. So you only wish you were. It's beautiful. But that gives you an idea. This is a one-parameter family of transformation, very much in the idea of D'Arcy Thompson. And D'Arcy start playing the game. Now there are plenty of ideas of different set of transformation done by D'Arcy that you can see and been discussed. He tries, he goes around and says, oh, these two look like that if I extend like that. Maybe the most interesting one from a mathematical perspective is his use of conformal transformation. So it's quite sophisticated actually, even for the time, or certainly for the time and for him. So in the plane conformal transformation, a transformation of coordinate that preserves angle. So he's going to compare, for instance, the human skull and change conformally to the skull of a chimpanzee, and you see the angle here conserved, or the skull of a baboon, right? So he's trying to see, to compare these different. And the question is that, is it a good measure? Is it really conformal? And this was put to the test by John Milnor, who is very well known in mathematics, being one of the very few winners of both a Fields Medal and a Abel Prize. So very serious mathematician who like very much the idea, and he realized, well, not quite, right? If you really take the skull and transform it, you have this object and not this one, so it's limited. But at least, maybe what D'Arcy wanted all his life is that he got the attention of the mathematician to look at his problem. So yes, it's not quite conformal, but wait. This is quite remarkable. Very recently, two groups of researchers, including Areski, who is one of the program organizers here, and Mitchison, which works at Sainsbury Institute also here in Cambridge, realized that in the growth of leaves, there are certain type of leaves that actually grow in a conformal way. And here is the measure velocity field of the petunia tobacco, and here is the matching conformal map. So it's quite remarkable, not just a first observation, but also for the simple fact that they realized, they went back to the equation, and they realized that if the growth is both isotropic and uniform in the plane, it directly implies conformality. So maybe after all, there was something very deep in D'Arcy Thompson remark about conformal map. Again, quite a surprise and very recent. But if we go back to skulls, for instance, how do we understand? I mean, these are extremely complicated shape in 3 dimensions, right? You have all this extra structure and all that. So how do we understand the diversity of this shape? Well, we can start by asking simpler questions. And the first question that we can ask is about the growth of the calvaria bone, the one on top, the main bones that you see, forgetting for the in first instance the growth of the facial bones. And as D'Arcy says, it's become at once manifest that the modification of Jaw's brain case and the region between are all portion of one continuous and integral process. So recently we look at this problem again, and we look trying to understand how does actually skulls grow. It's quite a fascinating process. In the skull you have, very early on, you have these sutures, which are very cartilaginous. And this suture is where most of the accretion process takes place. It's a bone, so just very much like the antler, it's a process of adding layers. There are actually 2 different processes of growth. First, you have to add layers, you have to increase the overall area, but you also have to remodel the area, otherwise the initial curvature of the small brain remains the initial curvature, and you have a very small patches. If you want to dilate a small sphere into a bigger sphere, not only you have to add material along lines, the suture line, but you also have to change the curvature of the bones that already deposited. So 2 growth process takes place there, and here is the active growth process about cells, but I'm not going to tell you in detail that. So in the growth process, you have the suture in the middle, the brain exerts pressure over the skull that is pulled apart, and is because of we believe, the stress stimuli that this process takes place. The bone are being pulled apart, and that's where the activity of the cartilagen takes place. And at the same time, as the pressure pulls here, some of the cell remove layers under and build new layers. And so when you remove a layer with high curvature and put a layer with smaller curvature, overall you decrease the curvature. Right? So the two processes take place. And you can see the effect in that in pathology, very clear. It's called the craniosynostosis. If you stop some of these suture line during development of for some reason, genetically or otherwise, they stop growing, they fuse early, then you obtain various shapes depending on where the process takes place. For instance, if you cut teeth line here, if you stop teeth line, you can only grow in length and not in width, right? So you can build a model out of all these ideas, trying to go from the mechanism into the shape. And the model that we built with Ellen Kuhl and the lab in Stanford is to have a simple model of a spheroid with different type of growth represented in the different suture line. So that you have growth in length in that direction, growth in width along the yellow, and the patch that are common in both have both growth. Right? And that's all we say. We just let the system run. And before we look at, okay, let's look at a normal human skull, and let's see how it grows, and you fit everything there. Right? So if you do that, this is the healthy brain. You fit everything after that, and then you start closing suture line, early fusion. And what you do, you get actually an excellent representation of the shape and of the different types. So you can go further and compare the cranial index, which is the ratio of the width by the length, and realize that this model recovers all that. So again, going from the mechanism all the way to the shape, right? Trying to realize that vision of D'Arcy Thompson. So let me go to the next stage now, mathematics, which is absent from D'Arcy Thompson by and large. But what is the mathematics that we really need to describe this process? The main point is that if you look at the growth process, different points in a tissue grow at different rate. And as D'Arcy says, it's obvious that the form of an organism is determined by its rate of growth in various directions. So that means that growth description must be a local description. You can follow a point here and look how it grows. Or more generally, if you take any body and extract a little sphere out of that, that sphere can become an ellipsoid. That's the most general way of describing it. That means that there must be a quantifier, an object that describes the growth of a local volume element in the most general case. Well, we know that G, mapping linear space to linear space, might be a tensor. So the theory that you need to do that, morphoelasticity, is a tensorial field theory. Right? It's part of a continuum mechanism with an extra addition that's due to growth process. Now, if you go down that path, you realize all the mathematics that you need. A local description of growth process actually requires differential calculus, of course, tensor analysis, and eventually, if you really want to put it on a real theoretical setting, on differential geometry. And the theory that you obtain in its most elementary or most beautiful form is very much on the same path than general relativity in terms of the differential geometry. It's the same type of object that we need to describe this theory. And this is the kind of theory that some people here and others have been working over the last 10 years only, actually, 10 or maybe 15 years. But the applications are quite nice, actually. You can apply that to many different systems. For instance, here, Ellen Kuhl in a lab has worked on application to the heart, to a skin graft, to the bones, to arteries. Here is other application that we've looked at in the past with students and collaborators. Maybe the most relevant one for the talk would be the one about the chameleon, because D'Arcy Thompson wrote a paper in 1905 about the chameleon. So you can push this theory. You can build a theory exactly like D'Arcy Thompson one from the basic. If you know growth law and basic mechanics, you can answer some of these questions. Maybe not all the questions that the biologists have, but you can explain the formation of structure. here I give you an example. We've been working recently, and other people have been working on this also here. The cortical folding. It's a problem that dates back from 1878, where Wilhelm His, who's heavily quoted and had a big influence on D'Arcy Thompson, that cortical folding is really a problem of developmental mechanics. So cortical folding refers that around 29 to 30 weeks in gestation, the human brain becomes folded. You have this high gyrification. And to go back to Le Gros-Clark, in his 1945 book here, to D'Arcy Thompson, describe the mechanics of cortical folding and say the sulcal pattern, this pattern, is largely determined by extrinsic mechanical factors operating during development. So it's forces that shape that. What is our understanding nowadays is that most likely the cortex grows faster, the cortex being the outer layer, grows faster than the inner layer. And that creates a buckling instability that creates either folding or creasing or something like that. And you can put that to the test. You can look at the growth theory where you have a thin film growing on an elastic substrate, and you recover most of the typical feature and most of the pathology also in this system. So you can put this idea to the test, and you can obtain some answers about basic pattern and basic folding mechanism. You can go one step further and say what happens when the brain is not flat or not a sphere but an ellipsoid, and you can relate different type of pattern exhibited on longer brain, dolichocephalic brain versus brachycephalic brain, like in the wombat, for instance. Right? You can start to understand some of these different patterns and play this game. So you can really push now this idea quite far, and we're very busy. Different groups in the world, including here, are looking at various aspects of this folding mechanism. So let me finish now the epilogue. In his epilogue, page 196, 1096, D'Arcy Thompson says, I've tried to show, he used the old form for show, you see, I've tried to show the mathematician a feel for his labor, a feel which few have entered and no man has explored. He's really calling for the help. He says, mathematician, no, go ahead and do work. This is the last photograph of D'Arcy Thompson in 1947, and you see him again with his beloved Nautilus. That was the subject of so many of his talks, and also a parable for his own life and work. So let's look back at the work of D'Arcy Thompson. What is his real contribution? It's hard to pinpoint, as he made fundamental contribution to mathematics, as many people claim. Well, you'll be hard-pressed to find a theorem of D'Arcy Thompson, a work that stands the time in terms of mathematics, apart from his classification of polyhedra. I don't think his paper is hardly quoted. So he's not known for his work in mathematics. Has he made any fundamental contribution to biology? Do you know any theory of D'Arcy Thompson in biology? Actually, it's striking when you talk to biologists, most of them don't even know the name. It's common household name for physicists and mathematicians. D'Arcy Thompson, people don't even know who he is or who he was. So it's not quite clear either. Is it a great work of literature, as some have said, like Peter Medawar, beyond comparison, the finest work of literature in the annals of science that have been recorded in the English tongue? Well, that's when he was writing for the book of his daughter. He said also in another piece that it was a Baroque masterpiece. So yes, you have this phenomenal writing paragraph that rise like big wave and crashing on the beach, you know. But on the other hand, sometimes you have these very long paragraphs that you never know where going and are written in 3 different languages and making obscure reference to Greek literature and so on. So it's very hard. It's not an easy read for sure. It's a work widely praised but seldom used in a review in 1942. So what is his contribution? Well, was D'Arcy a new man? Did he come and change the way people thought? Not quite. He really came at the end of the 19th century, at the last of the great natural philosopher. It's quite remarkable that as a real natural philosopher, he described rainbow and the shape of drops and many other physical processes very beautifully and very accurately. He was the last of the great natural philosopher, but I think he was also the first mathematical biologist. Right? What he did was he opened the door, he turned on the light, and tell people, mathematicians, where to look and what problem to solve. So he has great influence in physics and mathematics. You can see he's one of the only person that is cited in Alan Turing's seminal paper on morphogenesis, on the 5 reference, even though there is no place in the actual paper where the reference is mentioned, it's just in the references. It's another story as the paper came about because it was right at the end of Turing's life. It had a great influence of René Thom and the theory of catastrophe, and Jim Murray and the whole school of mathematical biology is very big influence. So its work really stands unique. He also has huge influence in art and architecture. You won't find his book in a biology lab, but you'll find his book in every architecture workshop, right? If you go to an architect, it's on the shelf. They've looked at it and been inspired. It's organic architecture for them. It's Le Corbusier, Zaha Hadid. It's all there, right? That's why they take the inspiration. So it's a unique work. It is not a foundational work, but it's much more. It creates inspiration for many generations. And I do not think that there is any other comparable work in the history of science for that. It's a source of inspiration, beauty, and it's true optimism for science. It's joy of science. Looking around you, it's here the beauty of science. And I think there is no better way to end that, give him the last words, one of the most beautiful words, almost on the last page. You see him in the field showing people. So the living and the dead things, animate and inanimate, we dwellers in the world and this world wherein we dwell, are bound alike by physical and mathematical law. Thank you very much.
We have time for as many questions as we want. Who would like to go first? Yes, Ben.
Have you tried your words raw on these pictures?
Have I tried white transformation?
Transformation.
I haven't tried any transformation, but the morphing would be interesting. I think the FBI has this kind of program, right, to age faces to see what somebody did.
And reconstruct that he's 3D.
Oh yeah, you can also now reconstruct the 3D shape, right? That's into his life. It's nice to see the evolution.
Did he imply that there was an evolutionary link between for instance, the fishes, which could be transformed one to another by conformal transformation? And is there?
So it's a very good question, and it's been studied in detail by people in biology who criticize on good ground the work of D'Arcy Thompson. It does not address that at all about evolutionary link. The criticism is that it doesn't look at the evolution of an animal through its life or compare it with ancestor. But if you look at the idea of the theory of transformation, it's really what other people are trying to do. What he's trying to do is link mathematically pieces of the phylogenetic tree without really saying so, right? But he doesn't go to the step of saying two that are close by in a certain type of metric should have common ancestor, which would be studied later on.
Is there a reason why these transformations should be conformal?
So there is a good reason, is that in 2 dimensions, if you look at the equation, you can easily simplify them and integrate them in the case of uniform growth and obtain that the solution are all the conformal transformation. Yes, it does work. It's kind of a surprise. And it's very easy to show. It's just playing with complex function.
So by uniform growth, you mean the growth is the same in any direction?
So yes, it's isotropic and uniform. The growth is the same at different places, and it's compatible. Yeah.
That's true, even if the growth is isotropic. If
the growth is isotropic,
it
yes.
doesn't have to be uniform.
No, actually, you're right.
More
Because
general class.
this example, you can see the velocity field is different, so the growth is not uniform. Thank you.
Any other questions or comments? Right. So before we close, I'd like to all of us to thank Alain for a wonderful lecture. There are a lot of students in the room, from the very young to the less young. And I am sure you have inspired all of them to become mathematical biologists. And congratulations on the publication of your book. I know you're looking for the next book, so I would like to suggest maybe Greek mythology as a subject of mathematics.
You'll have to wait 27 years.